this last portion of this course, we cover what we are going to be calling as important limit theorems, or important just call them that, important limiting theorems from probability theory. Some of them, there are many of them, but we will look at a couple of very important limit theorems. One of them I will prove because it is very easy, that is the weak law of large numbers, which is what we will take up first. These limit theorems, I will just also say what are these theorems going to be applicable to? They will be applicable to, right, a collection of random variables, IID random variables. So, this portion is going to be common to both theorems that we are going to talk about. So, we are going to consider a collection of IID independent and identically distributed random variables. You consider this collection, or i.e. let me just say x1, x2, x3. There you can have an infinitely large collection in this particular section. We are not going to we are not going to put an upper bound on the number of random variables we have. We can be, as I said, an infinite collection of IID. So, but the main point is they all have to be independent and identically distributed. So, with finite mean and variance, right, with the expected value of xi being this number mu and the variance of xi, both the mean and the variance of xi are finite, sigma squared. So, sigma squared is, in particular we want sigma squared to be finite. We do not want, right, we want both the mean and the variance to be well defined, right, and of course obviously for all I. That goes without saying, because whenever you say IID, obviously they have to have the same mean and the variance, and so we are going to call it as them as mu and sigma squared. So, this is common, right, this statement out here of IID and the mean mu and sigma squared, this is common to both the results we are going to talk about. So, the first result that we are going to talk about is the weak law of large numbers. There is also a strong version which we will not even mention here because it is somewhat technically advanced and we can't do it, we don't in this course, right. So, the weak law of large numbers is what we are going to concentrate on now. What is this weak law? So, this we will actually prove, right, state and prove. So, basically we are going to look at in both, actually even this point is sort of common. So, we are going to work, so what can we say about the behavior of the sum of these IID random variables. So, what we are going to say is consider this Sn is the sum of n of these random variables, small n of them. So, in all of these things we are going to consider this quantity Sn, which is basically the sigma I equal to 1 to n of the xi, that is sum of n of them, right, n of these. So, this quantity Sn, right, is the sum, and but what is more interesting than the sum itself is the sample average, right. So, given this given this collection of random variables xi, right, we can form the two random variables Sn, which is the sum. So, Sn is the sum. The sum of xi, the n of them, and Sn by n is a so called sample average. So here all I am doing is I am just dividing this Sn by the number small n, which is some deterministic quantity. Small n is entirely under my control. I can choose to take 10 of them, I can choose to take 100 of them, I can choose to take 1000 of them. N will of course be large in my application or in our application, but there is no there is nothing random about the small n, right. This n is a fixed quantity, right, n is non-random. It's fundamental, right, that's very important, that small n, right, is under our control and we get to decide, right, how big it is. Okay. So this Sn by n is called the sample average. Why is it called the sample average? It's called the sample average because if you consider this whole experiment, right, with where you generate or you find these n of these xi's, right, the values they take and then if you add them all up and divide by n, this is sort of telling you in some sense, right, telling us in some sense what is the average reading we get over the n trials, right. So the sample average is basically like an average over n trials. Okay, so let me write it here, or n observations shall we say. So we have averaged n observations, right, which correspond to the random variables xn, x1 through xn, and we have made all the readings and then we are averaging. So that Sn by n is called is therefore quite naturally the sample average. So it itself is a random variable. So note that Sn by n is a random variable with a mean and variance. So what are, right, is itself is a random variable, and this E of Sn by n is basically 1 by n E of Sn. This is basically nothing but mu, or let me write one more step here, it is n into mu divided by n, which is essentially equal to mu itself. Let me okay. So Sn by Sn will have a mean, right, which it increases linearly with n, right, it is n into mu, but Sn by n has a constant mean mu, the same mean mu of the xi, and that is true for all n. So the sample average, right, very easily it is shown that has the same mean value as any of the individual observations xi. Okay. But what about the variance of Sn by n? Turns out that the variance of Sn by n is 1 by n squared of, very important, this n squared of the variance of Sn. So the n squared is very important here, right, and the variance of Sn, the variance of a sum of independent random variables, as we have pointed out earlier, is the sum of the individual variances. So in this case the individual variances are all equal to each other, equal to sigma squared. So the variance of Sn is essentially going to be equal to n times sigma squared, and then of course divided by let me write go back to my different color, n times sigma squared, and then of course you are going to divide by n squared, and therefore this is identical to sigma squared by n. This is this is key. So it is very important to note here that the variance of Sn by n, right, the variance of the sample average basically does not grow with n, it actually decreases as 1 by n. That is extremely important because that is the, it is going to establish the law that we care about. And what is important is that this variance, therefore it tends to 0 as n goes to infinity. And therefore now if we apply Chebyshev inequality to Sn by n, so what are we going to do? We are going to apply the Chebyshev inequality, which we talked about earlier, in this week, or maybe whatever, right, where we talked about it just recently. To the random variable Sn by n. What do we get? The let me write it out here. The probability that mod of that is the sample average minus mu. So this this is the mean of the Sn by n, right. This is the expected value of Sn by n, this mu, right. The probability that the sample average takes values, the absolute distance of that Sn by n from mu, that the probability that this event happens, right, that this Sn by n taking a value epsilon away from mu in both directions, positive or negative, that is right, needed in the Chebyshev inequality. We know that this is upper bounded by, what is it upper bounded by? The variance of Sn by n divided by epsilon square. So this was what was done earlier in the course, right, and it turns out that in this particular case, this is right, this variance of Sn by n, this is a key thing which is going to be sigma squared by n divided by epsilon squared, and that is sigma squared by n epsilon squared. So sigma squared is some finite quantity, and epsilon of course is in our control. We can decide how big we want to make epsilon. Whatever, the point is, this is going to go to 0. This probability is also going to 0 as n goes to infinity. As you keep taking more and more observations, right, you find that the sample average Sn by n, right, it takes values, that is, i.e., the sample average this Sn by n takes values close to mu, right, for large n. In most instances of having these n trials. That is the meaning of this probability, right. So if you take take n trials of the basic experiment which produces the xi, right, and you calculate the sample average, you find that the sample average itself, right, is going to by virtue of this by virtue of this probabilistic statement, right, you can of course pick epsilon to be fairly small, right. The smaller you pick epsilon, of course, the larger you are going to have to make n to get the probability smaller to or as small as you want, right. Remember, the sigma squared by n epsilon squared is a finite number, and if you want to make it smaller and smaller, you have to make for a given epsilon, you have to make n bigger, right, and whatever you have to basically choose epsilon and n according to your application to get this probability as small as you want. But basically Sn by n is expected to take values close to mu, right, for large n, and as you keep increasing n, right, this fact will become more and more clear, right, that if you take the sample. So this is the justification for using the sample average as an estimate of mu. As a good estimate. So you don't know, of course, in a real life situation, you don't know the mu, right, the mean of the xi's, but right, if you want to estimate this unknown mean and you have a good good source of these xi's, right, which is reliable, right? You can repeat, you repeat the experiment any number of times, then you pick, take n repetitions, and then you average this, find the sample average, and it turns out that that sample average, right, in most trials you can say fairly confidently that that sample average is going to be very quite close to the underlying mean mu. Okay. So, this is a very important statement of probability and is actually very general, and this is the so called weak law of large numbers. Time justifying it, let me just take one example, which is basically, what example am I going to take? I am going to take the example of estimating an unknown probability itself, right. Supposing, consider an event A, right, such that the probability of the occurrence of that A is basically some number small p, right, and then consider n repetitions of the experiment that generates the event A. No, I shouldn't say generate, that includes the event A. Let me use the word include, right. That is, A is one of the possible events on the experiment, right, and it occurs with probability small p. Just for example, right, you roll a die and A could be the event that you get a 6 or something, and in which case PA will be 1 by 6, right, and we are considering n repetitions, n rolls of the die, or right, rolling n identical die, whatever, right. We are going to look at this very simple setup, right. So, we have n independent repetitions, right, and we are going to look at apply this weak law of large numbers to exactly this scenario, but how am I going to define xi? That is the key thing. So, xi we will now define xi as the indicator. This means 0 or 1 of event A on the nth trial, on the ith trial. The ith out of n trial, right. So, obviously 1 less than I can be any number from 1 to n. So, xi is the indicator of the event A on the ith trial, and so xi obviously is Bernoulli with probability, Bernoulli with parameter p, small p. In other words, that is the probability of xi being the value, taking the value 1. And of course, probability 0 with probability 1 with value xi equal to 0 with probability 1 minus p. So, this is basically, right, the textbook scenario of applying the weak law of large numbers, right, and Sn is now going to be the, if you look at this sum here, Sn equal to I equal to 1 to xi, this is, what is this going to be? This is going to be the total number of occurrences, right. Number of occurrences of event A clearly in the n trials, and Sn by n is going to be the relative frequency of the occurrence of A, or just let us just simply call it the relative frequency of A. Okay. So, this is the relative frequency of A, and Sn by n is the relative frequency of A, and Sn itself is the total number of So, if we now apply the law of large numbers, weak law of large numbers, What does this give us? What does it give us? So, all I am going to do is I am going to rewrite this this thing, right. I am going to come back here and redo that. Okay, what does it give? It says the probability, let me change the color here. The probability that Sn by n, it takes, now what is the let me say this, what is the expected value of xi? It is basically equal to small p and the variance of xi is basically 1 in p into 1 minus p. This we know from the binomial, the Bernoulli PMF. So, this p of Sn by n minus small p less than equal to epsilon, right. This event that the relative frequency is that it is this should be greater than equal to that the relative frequency is more than epsilon away from the sample mean, in this case p. So, this is a mu, let me do one more thing here. So, this is going to be the mu and this is going to be the sigma squared, right. So, this whole thing is now going to be, let me write it here, it is going to be upper bounded by p times 1 minus p divided by n epsilon squared by the weak law of large numbers, so, right. So, basically what we are saying is that this Sn by n is going to be now a good estimate of p itself. That is the bottom line, right. The sample average, that is which is here, which we identified as a relative frequency, going to be is close to this probability p. So, this exactly is the in most repetitions, let me use it color here, in most sets of, in most cases or most instances, shall I say, what is an instance here? An instance is each instance is going to be a repetition of n trials, right. Each instance is a set of n trials. So, you consider different sets of n trials, right, and you look at this relative frequency on each trial, each set of n trials, and what this weak law is saying is that the relative frequency in most cases, most instances, that is of these n trials, right, is going to be close to p. That is the expectation. I mean, that's our that's what we expect from this probabilistic statement up here. Okay, and this again we can put precise numbers based on the values of epsilon and n and so on, and basically this gives us the theoretical justification for using the relative frequency Sn by n as an estimate of p. So, that is the weak law of large numbers applied to applied to this binary case here, and bringing in using the justification, giving us justification for using this sample average, or which turns out to be in this case a relative frequency.